don't use that language in here. All right, I think we look good. You ready to go? All right, yeah, let me get you introduced. All right, well, thank you everyone for coming out. It's my pleasure to welcome Samantha Gilbert-Janizek, who is a sixth-year PhD candidate in the Astronomy Department and Astrobiology program at University of Washington. And her work addresses two forms of challenges that we face in searching for life on exoplanets with the Habitable Worlds Observatory, using retrieval models to accurately interpret habitability and biosignatures, and using planetary evolution models to quantify the null hypothesis of an abiotic Earth. So I will turn it over to Sam. Thank you so much for talking to us. And is your microphone on?
I think so. Can you hear me?
If someone can just post in chat if you can hear us okay?
Okay. Yes, I think we're awesome. Okay, thanks everyone. Thanks for the introduction, Joe. It's very nice. I'm Sam, everybody, visiting from University of Washington Astronomy and Astrobiology program today. Really excited to be here, really excited to see so many familiar faces in the room. So thanks for coming. Oh, hi, Robbie. Nice to see you. So what I'm going to be talking to you about today is a paper that came out earlier this summer, where we used a retrieval model to try to understand the relative strengths and weaknesses of transmission versus direct imaging when it comes to searching for habitable conditions and hopefully life on exoplanets. So as we all know, the ASTRO 2020 Decadal prioritized upcoming astrophysics missions that will use either transmission or direct imaging to try to characterize exoplanets located in the habitable zone of their host stars. More specifically, in these spectroplanetary atmospheres, we're going to be able to search for habitability indicators and biosignatures, which have spectral features at characteristic wavelengths. Where the definitive habitability indicator is liquid water on the surface, and the canonical biosignature pair is, of course, oxygen and methane. I think everyone in here already knows this information, but just in case, this particular combination of molecules is so important for any discussion of biosignature detection because on the modern Earth, methane and oxygen are kind of a smoking gun disequilibrium pair. Normally, they should destroy each other very quickly. So the only reason they should coexist in an atmosphere is because life is constantly regenerating them at the surface. Additionally, since ozone is a photochemical product of oxygen, it can kind of be used as a proxy for oxygen to give the ozone-methane pair as well, especially if, for whatever reason, your spectrograph doesn't have access to the visible part of the spectrum where oxygen absorbs. But when we say that we're substituting in ozone for oxygen, what we're trying to do is actually analytically use ozone to ultimately back out the oxygen content of the planet's atmosphere. So if we are going to successfully use ozone as a proxy for oxygen, it's really important that you can actually accurately infer the ozone abundance in the atmosphere so then you can reliably back out the oxygen abundance. So the only problem with this is that in contrast to oxygen, ozone is usually not evenly mixed in an atmosphere, which means that its abundance changes with altitude, which is what I'm showing you in this plot here. We've got a mixing ratio on a log scale on the x-axis, from left to right, really small abundances to really big abundances. And then on the y-axis, we have pressure in pascals, also on a log scale, where we've kind of flipped the y-axis so that the highest pressure is at the bottom of the plot. So you could almost think of this y-axis as showing altitude. When you start at the bottom of the y-axis, you're looking at the abundances close to the surface of the planet. And then as you go higher and higher up the y-axis, you're going higher in the atmosphere. And we're showing how the abundance scales with altitude. And so you can see that ozone kind of has this profile where the abundance hits a maximum at around 10 to the 3 pascals. This is called a stratospheric bulge. Whereas oxygen is evenly mixed throughout the atmosphere. Its abundance doesn't change as you go up in altitude. Okay, so if ozone's abundance changes with altitude, this can make it challenging to obtain a good abundance estimate for ozone from the planetary spectrum. And this could be especially challenging if we're not accounting for the vertical behavior of ozone in our models. And this goes double for exoplanets, where the shape of the ozone profile is going to be dependent not only on the creative and destructive processes that are happening in the atmosphere, but also on the photochemistry that will be induced by unique spectral energy distributions of the unique host stars, which could be something like an actively flaring M-DOR, for example, depending on your mission. Luckily, we're now closer than ever to being able to look for signs of habitability and life on exoplanets. So thanks to the recommendations of the decadal, the community is ramping up the development of a space-based direct imaging telescope called HWO, and we're currently working on determining the instrument requirements that we'll need for critical science cases. But in essence, the plan for HWO sounds relatively similar to the LUVOIR B mission concept, just with a slightly smaller aperture. The decadal also recommended the development of a probe-class telescope capable of transmission spectroscopy that would sort of be a spiritual successor to JWST. And this mission is similar to the proposed mission concept called the Origin Space Telescope, or ORIGINS for short. So starting with transmission telescopes like ORIGINS would measure the fraction of stellar light that passes through a transiting planet's atmosphere. So what's physically happening is the photons kind of skim the top of the planet's atmosphere on their way to us or our telescope. So ORIGINS would focus on observing rocky exoplanets orbiting M-stars in the near-infrared and mid-infrared wavelengths. So because its observing range would exclude shorter wavelengths where oxygen absorption features appear, ORIGINS has to use ozone as a proxy for oxygen. On the other hand, direct imaging missions like LUVOIR suppress the light from the star to directly observe the comparatively dim flux from the planet. And this is the plan for what HWO would do. So HWO would be designed to study rocky planets orbiting sun-like, aka FGK stars, in the infrared, optical, and ultraviolet wavelengths. And the way that direct imaging works, it captures photons that have reflected directly off of the planet's surface, meaning that in the spectra, you have encoded photons that have traveled directly from the planet's surface, as long as the planet isn't 100% enveloped by clouds. So the main problem that I want to address today is to help us understand how the differing strengths and weaknesses of transmission and direct images as tools for searching for life on exoplanets impact our ability to accurately and confidently assess habitability and biosignatures on these worlds. So to determine whether a planet is habitable or even inhabited, detecting key molecules like the ones I just mentioned certainly helps. But what would be even better is moving beyond merely detecting something like the yes or no presence of a molecule in the atmosphere to producing a characterization of the atmosphere that paints a more vivid, quantifiable picture of what the planetary surface is like and would allow us to confidently differentiate between living and non-living processes. So for example, both Venus and Earth have water vapor in their atmospheres, but from the perspective of habitability and life, of course, they are very different planets. So if you wanted to be able to differentiate them using remote observations, one extremely helpful line of evidence would be being able to tell that Venus has much, much lower abundances of water vapor in its atmosphere compared to the Earth's near-surface water vapor abundance. So to assess the capability of each mission to not just detect, but to characterize, what we really need are retrieval models. So can a show of hands in the room, who feels like they could explain how retrievals work to someone else in the field? Eleonora, that makes sense. Yeah, Amber, good. Okay, do you feel like you could explain it to someone not in our field? Okay, cool. I'm not sure about the second one, but for the folks who did not raise their hands for the first question, my goal today is to hopefully make this really understandable, really accessible. They're not as scary as they seem. So please do stop me and ask any questions about this. Hopefully this will help demystify it just a little bit. Okay, so to give a high-level overview of how retrievals work, we start with the telescope. So I think this is a schematic of like what HWO might look like. And the telescope gives us our spectral data. And based on the characteristics of the instruments, the amount of exposure time, this data is going to have error bars on it, right? Okay, once we have this data, the retrieval process can begin. And the way we start is we create an atmospheric state that we think could potentially fit the spectrum. So we're guessing abundances of key gases, we're guessing what the temperature of the planet might be. And then we use a radiative transfer model to create the high-resolution spectrum that corresponds to this atmospheric state. So basically, we take a gas atmosphere, and then we turn it into what that spectrum would look like. Okay, so retrievals solve what we call a Bayesian inference problem, where we just repeat this process many, many, many times. So we sample many different atmospheric states from what our prior beliefs about these atmospheres, about what these atmospheres might be like, and then we fit those corresponding spectra to the data until we optimize the fit. So this is what it might look like behind the scenes. We take a gas atmosphere, we turn it into a spectrum, we compare that spectrum to the data until we get the best fit possible. So in general, this fitting process can be very computationally expensive. So to save time, all retrieval models, including the one that we used in this study, make a set of simplifying assumptions. So for example, most models assume that all the gases in the atmosphere are evenly mixed, like I'm showing you in this plot. Their abundances don't change with altitude. And models that fit for cloud parameters will also assume things like the clouds are gray scatterers, so that they are also wavelength independent. This is really interesting to me, because I think that this means there's always kind of an intrinsic model mismatch when it comes to the complexity of a realistic planet, all of the physics, all of the interconnected processes that includes, versus what we can afford to include in our models, which obviously take computation time. So I think the key is to know what your spectrum is most sensitive to, especially based on your instrument requirements, so that you know what processes are important to include in the model, and then conversely, what are the processes you can afford to simplify, because the spectrum isn't sensitive to them anyway. So in the paper that this talk is based on, we do explore some of these simplifying assumptions. But today I'm going to simplify it a little bit because we only have 40 minutes. So in any case, we keep iterating over these simplified atmospheres until we find the spectrum, which represents the atmospheric state that best explains the data that we observed. So in a closed loop where you are simulating your observations, because we don't have real observations yet, obviously, we can go back and compare our retrieved atmosphere to the truth to basically see how well our retrieval model did. So to that end, we designed a retrieval study where we generate synthetic observations of the Earth, and then we apply a classic evenly mixed retrieval model to these observations to infer the atmospheric properties of these planets. And then we repeated that step with a vertically resolved version of our model to see if we can actually capture the vertical structure of ozone. And then once we get posterior distributions, that's what comes out of the retrieval model, for our transmission and direct imaging cases with the evenly mixed model, we want to compare our transmission posteriors to our direct imaging posteriors to determine how well we can interpret the spectra for these different observing techniques. And then finally, for comparing the evenly mixed and vertically resolved ozone models, we do what's called a Bayesian model comparison, where we use Bayes factors to quantify which model best explains the data, and if there is significant evidence in favor of one model or another. So a quick note about how we generated the synthetic data in this study. A lot of other retrieval papers will go through a process where they use the same model to generate the synthetic data and to fit that data. So that means assuming that the atmospheres are evenly mixed, that they're isothermal, even for just producing the data that we're ultimately going to fit. And this is a completely defensible, reasonable practice, I think, especially when you're in a regime where you're trying to control for model biases and assess things more like, what's the SNR we need to detect this, or what's the long wave cutoff that we need to be able to detect so-and-so molecule. Completely fair and makes sense. I think we did something a little interesting in this study where we kind of switched it up a bit. We still use the same model to produce the data, but we give realistic inputs to the model to generate the synthetic data. Our model that fits the data is still pretty simplified. Again, we want it to be nimble so we can explore a lot of parameter space. But we're kind of encoding the model mismatch that we will encounter when we get observations of realistic planets, and then we have to use a simplified model to try to explain them. So to make the synthetic data as realistic as possible, we included wavelength-dependent ice and water clouds, just like we have on the Earth, where there were reflectivity changes with wavelength, which is what I'm showing you in the bottom plot there. And then we also use realistic temperature and molecular abundance profiles that change with altitude, just like they do in the real Earth atmosphere. Like I said, we'll still use a simplified model to fit the data, but now we're allowing the spectrum that we're fitting to encode all the complexity that a real planet would have. So the main axes along which we'll be grading a posterior are accuracy and precision, where an accurate distribution has a peak that lines up with the true value. So that's kind of the upper left segment of this grid. A precise distribution is very narrow, expressing a high confidence in a particular value. But of course, an accurate distribution need not be precise, it could be pretty broad, and a precise distribution need not be accurate. You could have a really narrow distribution that's biased really high or low compared to the truth. In an ideal world, obviously, our posteriors would be both accurate and precise, so that we're confidently retrieving the true value for an atmospheric parameter. But also not all posterior distributions will take on the shape of a normal distribution, like I was showing in that last slide. And these distribution shapes also mean something. So for example, some distributions can be flat throughout most of the range. And that would mean that we haven't gained any additional information from the spectral data. This is kind of like a worst case scenario, these flat posteriors. But you can have another version of this where it's flat through most of the range, but then it kind of falls off precipitously at an upper limit value. And these upper limits can also be useful in the absence of a detection, because they tell you that if you had more than that upper limit of a gas, you would have detected it in the atmosphere. Okay, so to make the comparison between transmission and direct imaging a level playing field, we choose the optimal observing scenarios for each. So in reality, there likely aren't many, if any, mutually amenable targets for these mission concepts. But I will address the issue of mission synergy a bit at the end. So for transmission, we have a modern Earth-like TRAPPIST-1e, and for direct imaging, we have an Earth twin at a distance of 10 parsecs. And we ran that Earth twin with and without clouds in the synthetic data. The paper also explores a false positive case for the transmission cases, but for the sake of time, we're just going to focus on comparing these. Okay. So we'll start by comparing posteriors from our retrieval model for transmission versus direct imaging. And I want to orient us a little bit on reading these plots because there's a lot going on. Okay, so on the x-axis, we have mixing ratio on a logarithmic scale. So depending on what the bounds of your x-axis are, you could be spanning a large range of abundances. So in this first plot that I'm highlighting, goes from -10 or 10 to the -10 all the way up to 0 or 100% of the atmosphere. So this is a really, really broad range. And then on the hidden y-axis where I don't have any values, this is sort of like your normal counts that you would have for a histogram. So what the teal is showing you is the posterior we got from the retrieval model. And it's showing you which abundances along the x-axis were most likely to explain the spectrum. Okay. And then on the top, we have the 1 sigma range of abundances with the median of the distribution, but translated into linear form. Sometimes the log form can kind of disguise how broad the distributions are. So this is kind of trying to make an effort to translate it to something a little bit more comprehensible. Okay. And then there's also this white line on the plot. This white line on the plot is the true profile from the atmosphere that we use to generate the synthetic data and then that we fit to produce these posterior distributions. Okay, so this white line has the same x-axis as the posterior distribution. It's showing you how the abundances change, but this time the y-axis for this line isn't counts, it's pressure. So it's showing you, if you look at the left y-axis, how the abundance changes with pressure in the real atmosphere. So with this line over the posterior, we can kind of compare where the posterior distribution peaks to the true profile and kind of examine if we're doing a good job at nailing down some abundance along the true profile. Okay, so here we're starting with water vapor for the transmission case, where we've got the retrieved posterior in teal, like I said, and the real atmospheric profile that we inputted in white. And what this posterior shows us is that we retrieve a broad water vapor distribution that is biased a little bit low relative to the true stratospheric water vapor abundance. And what I mean by that is that the peak of the distribution is a little bit to the left of the true stratospheric water vapor profile. So this would suggest that we're most closely probing the water vapor in the upper atmosphere and not the water vapor at or near the surface with transmission. Okay, so this broad range of water vapor abundances that we retrieve is actually consistent with both Earth and Venus water vapor inventories to within 1 sigma. So what that suggests is that it would likely be hard to use water vapor in this setting to differentiate between a desiccated planet like Venus and a relatively more water-rich planet like Earth with transmission. So for the direct imaging case with clouds, we retrieve a really precise distribution of water vapor that is consistent with the true water vapor abundance at around 5 kilometers, an altitude of 5 kilometers in the atmosphere. And if you don't have any clouds, then you can actually probe even a little bit closer to the surface at 3 kilometers. I think what's really notable here is how we retrieve such a narrow range of water vapor abundances, which suggests that you actually could easily distinguish this planet from a Venus-like world, even if you did have clouds in the atmosphere, just because you're getting this really confident answer that you have relatively high water vapor abundances in the atmosphere. And this is with direct imaging. Okay, so turning to our biosignature gases, for transmission, oxygen is unconstrained with an Origins-like mission, but that's no surprise. I already told you that we don't have access to oxygen absorption features in Origins-like spectra. And we know ozone has to be our oxygen proxy. But our retrieved ozone distribution is broad, and Thea Kazakis showed in a paper, I think last year, a couple years ago, that even in the ideal circumstances, it can be really difficult to translate a photochemical product like ozone into its source molecule, oxygen, especially when you're trying to consider the particular stellar spectrum that you're dealing with. For methane, we retrieve a distribution that sits decidedly higher than an estimated maximum amount of methane that you might generate from a really efficient abiotic source like serpentinization. And that's a geochemical process where water runs over rock and produces methane. So this suggests that it's potentially less likely that the methane we've observed in this spectrum was produced by an abiotic source, but more theoretical studies into methane abiogenesis would be super helpful for establishing more confident upper and lower limits on abiotic methane generation. Okay, for direct imaging of the clear sky planet, our Earth-like oxygen is precisely constrained, and we can easily rule out abundances smaller than 5% of the atmosphere or greater than 30% of the atmosphere. So if you pay attention to the x-axis on this oxygen plot, you'll see that the bounds are actually very narrow, even in log space. It only goes from 10 to the minus 1 to 10 to the minus 0.5. So pretty well-constrained distribution. So this suggests that we may be able to use oxygen as a strong biosignature, even on its own, without additional molecular context, as long as you could rule out false positive scenarios. And the main false positive scenario for modern day abundances of oxygen are low non-condensable gas inventories in the planet's atmosphere. So basically our atmosphere has 78% nitrogen. This is relatively heavy, and this helps keep water vapor close to the surface. On a planet that doesn't have something like 78% nitrogen, water vapor isn't held close to the surface, and it can kind of float up higher into the atmosphere, where it's much easier for the star to zap those water molecules apart. And once it zaps those water molecules apart, you can make oxygen in a way that doesn't require life at all. So the way that you would want to assess this is try to determine what the non-condensable gas inventory of this planet is. And you could do that with direct imaging spectra by fitting for the Rayleigh scattering slope, as well as fitting for the surface gravity of the planet. We also retrieve a very precise ozone distribution which could help us further validate the amount of oxygen that we're seeing. If you use something like a photochemistry model to post-process these posteriors and calculate the range of oxygen abundances that could produce the abundance of ozone that we retrieve. Lastly, though, methane is unconstrained for modern Earth-like fluxes around a G-star. But again, this isn't a huge surprise. We know that this is a challenge for direct imaging. And this is something that we're also exploring in the HWO retrieval subworking group. So there might be other Earth through time cases, and especially if you go to higher SNR, it might be possible to get some information about methane from the spectrum. Okay, so I just showed you the retrieval of biosignature gases for the clear sky direct imaging case, but now I want to address the cloudy case because some funky stuff came up when we did include realistic wavelength-dependent clouds in the synthetic data. Okay, so once you have these super realistic ice and water clouds in the synthetic data, suddenly you have another source of opacity that you need to fit for in your retrieval. We did something a little bit weird where we didn't actually retrieve cloud properties. So clouds are in the data, but we're not allowing the model to fit for them. And this kind of helps expose some of the biases that occur if you're not properly accounting for a realistic cloud. So one interesting thing that we found, it does seem like our spectrum is sensitive to the wavelength dependence of the clouds. And one way that we know this is we had a really poor fit to this CO absorption feature that's sort of right in the wing around 1.5 to 1.6 microns. The fit is visibly bad. And the retrieval significantly overshoots the true value. The posteriors peaked at a much, much higher abundance than what the true profile would suggest. So this means the retrieved distribution significantly overestimates the abundance of CO in this atmosphere. And the reason that this happens is basically because of some of the very strong absorption features that realistic clouds have. So for example, there's a really strong ice absorption feature right around 1.5 microns. So that ice absorption feature is overlapping with this CO absorption feature. So since that ice cloud absorption is in the data, but we're not letting our model try to fit for it, the model tries to compensate by cranking up the CO abundance to explain the cloud-related effect in this part of the spectrum. Similarly, we can look at what happens to water vapor when you have water vapor clouds in the data, but not in the retrieval model. So in the plot on the left, the white line represents the true spectrum with wavelength-dependent clouds and a water profile that has a distinct cold trap, right, where the abundance scales with the decreasing temperature as you go up higher in the atmosphere, which allows water to condense, and you can form clouds at like the tropopause, for example. Okay, and then we've got this realistic water profile that corresponds to what we see on Earth here on the right, where you can see that cold trap behavior. So by contrast, this aqua teal line is the spectrum you get when the forward model applies an evenly mixed abundance corresponding to the cloud top water vapor abundance in the true atmosphere. So as you can see with the aqua line on the right, that's showing you that the cloud top water vapor abundance is much lower than the near surface water vapor abundance. And then lastly, we have this yellow line here, which is the spectrum you get when the forward model applies an evenly mixed abundance, but now corresponding to a near surface water vapor abundance in the true atmosphere. So now we're taking the much higher water vapor abundance closer to the surface and producing a spectrum and comparing that to the realistic spectrum. So when we compare these different forward model spectra in aqua and yellow to that true spectrum in the white line, we see that the spectrum generated with the lower cloud top water vapor abundance, that aqua line, is kind of a decent match to the bottoms of the water bands. So if you look around 1.4 and 1.9 microns, the aqua line does a much better job of overlapping with the white line, the true spectrum, than the yellow line does. But obviously you can see as well that it isn't a great fit to the width of the absorption feature here. So this is kind of the part of the spectrum spanning from 1.5 to 1.8 microns. The aqua line kind of overshoots it, especially in the lower wavelengths. It's a little too, the real spectrum is a little too narrow compared to the aqua spectrum. However, the spectrum generated with that higher near-surface water vapor abundance, that yellow line, is a pretty decent match to the width of the absorption features in the true spectrum. So the spectrum corresponding to that near-surface water vapor abundance, it's missing the bottoms of the bands, but it's doing an okay job at fitting the width of the absorption features. Okay, what this possibly indicates is that reflectance spectra could be sensitive to water vapor at both the cloud top and the near surface, as long as your planet isn't 100% covered by clouds and the photons do have a path to the surface. I think this result nicely complements another retrieval study put out a couple years ago by Mario Damiano and Renyu Hu, where they actually did retrieve the water vapor abundance at and below the cloud deck. Okay, as for trying to fit the vertical behavior of the ozone profile, we've got the transmission results on the left and then the direct imaging results on the right. What we're seeing here is that transmission is effectively insensitive to the vertical structure of ozone. So we tried to fit for 3 different abundances along the ozone profile, one kind of close to the surface, one around where the stratospheric bulge occurs, and then one higher up in the atmosphere. And with the error bars on those points, which we got from the posteriors for each of those abundances at each of those locations along the profile, they completely overlap. I think I lost Zoom. Oh, okay. It says that I'm connecting to something. Okay, never mind. Okay. All right, cool. Sorry for the interruption. Yeah. Oh, okay.
You did lose Zoom.
Okay, let me get back on there. Sorry, everybody.
I'm sorry. It was internet by chance?
Maybe. Oh, you know, like it's decided that it was time to update.
Oh, of course it did.
Which is very fun, yeah. No, it's my laptop. It'd be fun if it literally just does not let me come back. Maybe I did lose internet.
Weird, it still shows you on your guest there.
Yeah.
Well, while this is updating, is there any questions for anything for Sam in the first part of this talk? Feel free to raise your hand either online or in the room. Try to get the Zoom connected again. Oh, okay. That's fair.
It's a good time to get some snacks. I think he's smart for that.
I'm also like, do you have your flag or something like that?
Maybe, but something's like gonna happen with the fonts because they're like, you know, it's really vain.
Just a quick one, since we have quick. Did you do the whole spectral range that was from the LUVOIR report, and did you assume a certain SNR profile?
Yes, so exposure time of about 40 hours if you're assuming LUVOIR B aperture, 10 hours if you're assuming LUVOIR A aperture.
Okay, and did you include variations like with the instrument throughput from the LUVOIR model and things like this? Okay.
Everything from the final report is what was used,
gotcha. And the full spectral range?
Yes, correct.
Okay.
Well, we try to debug technology. You can ask. We're still waiting for Zoom to, Oh, sure, yeah. I can multitask, I'm good. Okay, go ahead, Ravi.
So you did show a spectrum of water with surface and cloud top just now, I think, in one of the slides.
Try to get it back up in a second.
Right, whenever. So how do you distinguish between those two if you just have one spectrum? How do you know where is it coming from the cloud top or on the surface?
Yes, I think that's a good question. I think it would be super helpful if we did have temperature information, which generally direct imaging spectra aren't super sensitive to. But I think Amber did some work showing that if you go up to high resolution, you can get temperature information, right?
Right, from water vapor sensitivity to, like, the opacities are temperature dependent, and since water vapor is such a dominant species, sometimes there's temperature information encoded in there, yeah.
Yeah, so I think it would be model dependent again, and you'd want to be really careful about what assumptions you're putting into that model, but I think you could use like an adiabat to try to fit the water vapor profile and have that tied to the temperature that you're trying to fit as well. But I think that's a good question. For everyone?
I'm not sure if anyone.
Is it not my fault?
I don't think it's your fault.
Yes.
I think it would be a USB edit from mine. I mean, it will still look okay and see if you
True.
want to send it, or if you can send it to a long one.
I was going to see if I could hotspot it, but I actually don't think.
Oh, that's actually a really good idea.
Thanks, Joe. Sorry, everyone. Oh my God.
I probably should have helped y'all first.
All right, let's go.
All right, got this. So sorry.
No, please.
It's bad.
It happens. It's totally okay. Well, once Gmail connects, then we should be good to go. Bro, you got this.
Oh, that was good.
Yes.
Okay.
I hope we don't blow up your data.
Oh, no,
though.
I got that postdoc unlimited data.
Wow.
Yeah,
We did it! Okay.
hey, look at that.
Yes, okay. Can everyone hear me okay again? So sorry about dropping out. The Wi-Fi went out here.
Yeah, I have a question.
Oh, you have a question? Let me just test.
Okay, thank you. So sorry, everybody. Okay. You see?
Yes and yes. Eleanor, did you want to ask a question real fast
Yeah,
before we
go
get
for
started?
it.
I don't know. So, no, it's about this slide, so that's why. So, the way you took these 3 points, are they connected with each other, or are they just points?
Yeah, so I think what we required is that they have to monotonically increase when they get put into the forward model, if that makes sense. So we wouldn't want the model to go from high pressure close to the surface and then jump up to the top and then try to fit the middle. Yes, so that's like the one thing we kind of enforce, that the pressure has to decrease with the profile. And we did a few different versions of this vertically resolved model where we like kind of pre-selected the pressure points and cheated, and then another one where we let the model fit for different pressure points and different abundances at those different pressure points. Oh, yeah, that's right. And I think in this case, we kind of get away with it because we're not looking at the higher resolution cases where you can probe temperature in the spectrum. At the resolutions we explored, we were basically completely insensitive to temperature anyway. Good question, though. Okay, let me try to get back to my spots. I think we were talking about the plot on the left, and you can see that basically all the error bars overlap. So you could effectively fit this profile with a straight line, which suggests that transmission isn't at all sensitive to the vertical structure of ozone. Whereas on the right, it's not super confident. It's a very, very weak sensitivity at the exposure time that we used. But you can kind of pull out the stratospheric ozone bulge. And the reason that we're able to fit for that is thanks to the UV Hartley band. So if your spectrum does go down into the UV, especially if you cover like I think 0.3 microns, depending on your error bars there, the model can tell the difference between an ozone profile that increases as you get to the stratosphere versus one that does not. And you can see that the version of the model that doesn't fit for this bulge does a worse job at fitting the spectrum. And I might have a plot in a backup slide here if you want to see that. So what this suggests is that maybe a direct imaging telescope that does have UV coverage could maybe even supply bonus context for important biosignatures like oxygen. And I think this could be particularly important as well if we are really limited on our ability to constrain methane, especially for Earth through time-like cases with direct imaging. Okay, so for our main takeaway points so far, constraining the near-surface water abundance for assessing habitability is probably more promising with direct imaging than it is with transmission. And direct imaging may also be sensitive to the cloud top water vapor abundance, as well as wavelength-dependent cloud properties. Oxygen is a good biosignature to aim for constraining with direct imaging, but methane may be a challenge in the near IR for at least Earth-like fluxes around G-type stars. Giada actually showed in a paper a few years ago that you can get a photochemical enhancement of methane around K stars. So even if you have the same Earth-like flux on the planet, the stellar spectrum, the spectral energy distribution from the star will allow that abundance of methane to build up higher in the atmosphere. So that can make it easier to constrain methane with direct imaging. And lastly, we have that methanogenic biosignatures will probably be easier to constrain and assess than photosynthetic biosignatures in transmitted light. Okay, so obviously the best thing would be able to use transmission and direct imaging to characterize the same planets. So the weaknesses of one observing technique kind of cover the strengths of the other, or could be covered by the strengths of another technique. But there aren't going to be a ton of transmission targets that are amenable to direct imaging. For example, TRAPPIST-1e doesn't have sufficient separation from its star to be able to clear the inner working angle of HWO, but there are other potentially complementary missions both in space and on the ground, and so I'll touch on that super briefly at the end here. Okay, so in this plot here, I'm showing some shared targets between the LUVOIR B mission concept and the LIFE mission concept. Since I made this plot, there has been a more refined HWO target list, but it significantly overlaps with the LUVOIR B target list, maybe just a few less stars due to the smaller aperture. And the LIFE mission concept is a space-based thermal emission telescope being developed for the European Space Agency. And if you look at this plot, you can see that there's a nice spread of spectral types here. There are several M stars and several C, K, and F stars. And in particular, as I said, Giada's 2019 paper, K-dwarfs are particularly interesting for biosignatures because you can potentially get a photochemical buildup of methane, but also a really nice planet-to-star contrast around sort of M stars, but without all the super intense XUV. So K stars could be really cool for this. Okay, so we can take one of these K stars shared between the LIFE and LUVOIR target list, slap an Earth around it, and perform a LIFE-like emission retrieval and a LUVOIR B-like direct imaging retrieval for the same exact target, and kind of compare what we're able to extract from the data using two different observing techniques, but for the same planet. So we're looking at results for a proterozoic Earth. So the methane abundance is slightly higher than the modern Earth cases, and the oxygen abundance is slightly lower. And these results suggest that thermal emission can help compensate for the relative insensitivity of direct imaging to surface temperature, at least for the resolutions that we explored. So on the left, we see that thermal emission observations allow you to very precisely constrain the surface temperature of the planet, whereas direct imaging, again at the resolutions we explored, really can't tell us much about the temperature of the planet. Similarly, thermal emission may be more sensitive than direct imaging to Earth-like abundances of methane. So direct imaging gives us a methane upper limit, which is okay, that is useful information, but it's not exactly a detection, and it definitely wouldn't help us rule out that the planet has sort of the lower abundances of methane that you might expect to find due to an abiotic source generating that methane on your planet. By contrast, the thermal emission gives us a much more tightly constrained distribution. It's biased a little bit high, so that is something to note. Okay, then really quickly at the end here, mostly focused on space-based missions. The paper only talked about space-based missions, but obviously large ground-based observatories are also going to play a role in detecting and characterizing potentially habitable exoplanets. So one of these observatories is the Giant Magellan Telescope, or GMT, and in particular, it's going to have this instrument called GCLEF on it, which stands for GMT Consortium Large Earth Finder. And it's going to have a very, very high resolution Echelle spectrograph that will hopefully see first light at the start of the 2030s, hopefully. It'll also have a chronograph, which means I think it can do visible spectroscopy of nearby transiting exoplanets. So this access to the visible part of the spectrum means we no longer need to rely on ozone as a proxy for oxygen, because we can get a really beautiful high-resolution detection of the narrowband oxygen feature at 0.76 microns. So this plot here is a simulation of what Earth-like abundances of oxygen might look like measured by the GCLEF spectrograph. Something else really cool about GMT is it's going to be capable of taking EPRV, or extreme precision radial velocity measurements for detecting Earth-sized planets around sun-like stars, possibly a full decade before HWO launches. So this means that ground-based observatories like GMT will probably give us a sizable head start on at least building up population-level statistics about Earth-like planets around sun-like stars, and maybe even Earth twins located in the habitable zone. Even if these targets aren't amenable to characterizing with direct imaging once HWO does launch, these population statistics are still super critical for science case development. Okay, so in addition to those main takeaway points we went through before, which are still up on the slide, just wanted to emphasize that retrieval models are powerful tools, they're not scary, and they can help us assess the potential yield of future missions, as well as potential synergies between different future mission concepts. And with that, I will take your questions.
Awesome, great talk, Sam. So yeah, we have plenty of time for questions. So if anyone in the room has any questions, feel free to raise your hand, or anyone online, also feel free to raise your hand.
I think there were some messages in the chat.
Yeah, I'm watching the chat. I think
Okay,
we're okay right now on that.
All right.
Yep.
I just have a quick comment just to make sure about life that's actually not organized by the ESA.
Oh,
by ESA.
my
It's
bad.
just
Okay.
it's just a lot of European contribution, but right now there is no ESA
Okay. Is the hope that there will
affiliation.
eventually be ESA involvement?
Obviously, of course, but that's not, you know, they're just doing the work, and that's not, at this point in time, there's no ESA involvement in that.
Thank you for the
Yeah,
clarification.
sure.
My bad. Yeah.
Call it a European-led mission concept,
Yeah.
but, you know, it's like saying something is blessed by ESA or NASA, it's like a sensitive political
Oh,
thing.
okay. Okay. I'm sorry.
No, just a comment.
Sorry, getting bombarded by all the retrieval modelers in the room.
No, this is heaven for me. Like, thank you for coming.
Yeah,
I'm
no,
excited.
there's so many like discussion points and like trains of thoughts that came about from this. So I'm excited and looking forward to talking with you later on in the afternoon. So my question, I wanted to ask again about this sort of like sensitivity to the actual vertical profile and structure, particularly for the ozone, because you mentioned the UV absorption there, and I was wondering, have you done sensitivity tests to look at the difference between the visible, like the Chapuis band for ozone versus the UV, and like whether or not there's a case for that?
Okay, so I ran Jacobians for the spectrum. And what's really cool is the Chapuis band is kind of sensitive to like where the it's sensitive not throughout the entire column. It's sensitive kind of to the part closer to the surface, but the Hartley band is sensitive throughout the entire column. And so that's why it's kind of like the key part of the spectrum, where if you do want to try to resolve the profile, that's the feature you need to nail. Yeah, yeah.
You're fine. Does anyone else have any questions for Sam? Go ahead online.
Oh, hi. Can you hear me okay?
Yeah, we can hear you. Go for it.
Yeah, my question was regarding the clouds. So are you modeling the cloud layer as a single globally present cloud layer, or are these cloudy patches with uh, clouds of different opacities at different heights?
So I'm having a hard time hearing.
Yeah, we're having a little bit of trouble hearing you. Do you mind repeating that? I'm going to turn it up a little bit in here. Just your question again one time.
Oh, yeah, sure. Is it better?
Let's see here. Okay, can you try it now?
Yeah, hello.
Yes. Try it again.
Awesome. Let me. Okay, I think I've changed my microphone settings. I think it should be better.
Yeah, I think that's worse.
Would they mind typing?
Yeah, do you mind just typing your question in chat?
I'll
Sorry, we're having a
I'll
little
just
trouble
type
hearing
it.
everything.
Yeah, awesome.
Yeah,
No
no
worries.
worries.
I heard that it was about clouds, though.
All right, well, someone's typing that up. Does anyone have any questions in the room? Or Avi?
Yeah, great talk, of course. Is there a reason you did not look at emissions spectra with a origins type? Only because if we're looking at sort of future emissions, and this is the hard part that you stuck with, which is great, stuck with very specific instrument parameters in that sense, which is fine. But
yeah, not a trade study exactly.
yeah,
right?
but the origins definitely would go into the mid-infrared more than with, as you say, more sensitivity and so forth. Is that something you looked at, even on the side or anything, or was there?
Well, how far into the mid-infrared are you thinking?
Well, so the origin study went out to 20 microns in the mid-infrared.
Yeah, we went up that high. Yeah.
In emission.
Yeah, I'm not sure that we actually included that source in the spectra. I'd have to go back and check.
Okay.
But I mean, the real reason that we didn't also do an emission case is the paper was already published. Yeah.
Okay. Yes.
Yeah.
Totally
But
makes
I
sense.
think it would be cool to go back and do that as well. Yeah.
Okay, great.
All right, so someone was asking a question regarding how you were modeling the clouds. Is this a single cloud global layer at some altitude, or do you have cloud patches with clouds of different opacities at different heights?
Okay, so we are 1D modelers, so we are choosing an altitude for the clouds, and the altitude that we choose is motivated by self-consistent photochemistry and climate models, but those are 1D and predict different cloud heights than 3D models do. So there's definitely a caveat there. That being said, we're modeling 50% clouds, and the way that we do that is you calculate the spectrum without any clouds, then you calculate the spectrum with 100% water clouds, 100% ice clouds, and then you sort of linear combine those spectra according to the cloud fraction that you want to have. So for 50% clouds, you take 0.5 of the clear sky spectrum plus 0.25 times the 100% water vapor spectrum plus 0.25 times the spectrum with 100% ice clouds. Hope that answers the question.
Yeah, just let us know if you have any follow-ups. There's another question in chat that says, do you expect BlueVar to deliver 10 orders stellar light suppression? So far, the best results barely reached 4 orders. And there's another question, but I'll pause there.
Yeah.
Yeah.
Completely fair. I mean, to me, that sounds like a technology maturation question, which is on all of our hearts and minds. I think as we're, trying to make sure that the telescope is capable of the ambitious science that we want it to do. And I kind of feel like when I ask other folks about this who actually do talk to the engineers, it's really like a cross your fingers. I sure hope we'll be able to hit those contrasts, right? Because Earth-like planets in the habitable zone are dim. So I think that's kind of just a necessity for doing this kind of science. And it's scary, I agree. I think it sounds like coronagraphy will have to come really, really far to be able to achieve those goals. So I would say, yes, I agree, and it's scary, but I'm very hopeful and optimistic, yeah.
And then the other question was, transmission observations are combined with certain data analysis techniques. These could improve significantly. Could this potentially change your conclusions?
Could they be more specific? Like, are we talking about stacking different spectra, for example, to achieve higher SNR, or?
Yeah, feel free to come off mute if you'd like.
So, for example, one can, or at least that's the thing I'm working on now, is direct recovery of the transmission spectrum of planetary atmosphere, avoiding cross-correlation and various machinery for removing stellar features. And so that seems to be much more promising in terms of preserving the planetary signal.
Okay. Yes, I would say that the transmission spectrum we produced, or the spectra that we produced in this study, were already very, very optimistic and already assume that you could completely clean out stellar contamination from the spectrum, assume that you can stack spectra to get higher SNR. Already pretty optimistic with the hope that, yeah, these techniques will improve. But certainly if we were trying to do like a JWST type study, you would want to be less optimistic with the spectra that you were simulating. So good question.
Okay, thank you.
Great, thank you. Let's see, a final question for Sam. Well, I will take a shot at one. I don't believe in atmosphere, so I don't know what I'm talking about. But you talked about clouds, and I often hear people talk about hazes. So have you looked at what that does to these results here?
No.
Okay, perfect, great, thank you.
So I think Giada has shown in her pale orange dot papers that there's kind of like a CO2 to CH4 ratio where hazes are more likely to form. For the planets that we did here, luckily, don't have those favorable ratios for haze forming. And I think in a lot of cases, even when people do model like the Archean Earth, which we think could have had a haze, they'll tune the ratio so that it's just low enough so that you don't have to include the haze. Which I think is my roundabout way of saying that, yes, I think hazes are really important as well. I think Peter Gau's done really, really cool work about those sorts of like more exotic aerosols. And I feel like retrievals are in their infancy a little bit. Like we're just starting to gear up, getting good at running these models, getting really good at understanding how our assumptions in the models affect our interpretation, rethinking those assumptions. And I think there's really exciting developments on that front. So like Amber's doing retrieval model intercomparison with cuisines, which is so cool and so important. I think that's going to yield a lot of helpful information about different model assumptions. And then also I would plug the HWO sub-working group. Lots of early career people like me, like Amber, Natasha, doing really cool retrieval work and getting the chance to like talk to each other on the annoying technical jargony level that nobody else wants to hear. That I think is also really helpful for like advancing this methodology. So I forget what the original question was.
That was perfect.
Yeah.
Awesome. Well, that puts us right at the hour, so let's thank Sam again for the great talk.
Sorry about the tech issues, sorry.
And I think Sam's around this afternoon and maybe later in the week. I'm not sure, but definitely this afternoon.
Area, and I can definitely meet on Zoom, of course, anytime. Cool. Yeah.
Yeah. So if you want to meet with Sam, please get in touch. But I'm going to end the meeting. Thanks everyone for coming out today.
Thanks so much, everybody.